Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Laden Neurotech.
Hello, everyone. Welcome to the Neural Implant Podcast. Today's guest is Jacob George, and he is a professor at the University of Utah, and he works on, he's in the Utah NeuroRobotics lab, and he works on the Luke arm and doing all this really cool stuff to basically integrate BlackRock and all these, very cool, futuristic sci-fi sounding things. And Jacob, do you want to introduce yourself better than I just did?
Sure, yeah. So I'm an assistant professor at the University of Utah. My appointment's actually joint between the Department of Electrical and Computer Engineering and the Department of Physical Medicine and Rehabilitation. And we're actually housed in the new Craig H. Nielsen Rehabilitation Hospital, which is a fabulous new building serving a large portion of the U.S., actually the largest percentage of the U.S. by land mass. We have people from all over the world that fly in from remote areas in like Montana and all sorts of stuff. Anyway, we have a really fantastic new facility, and it allows us to do some really cool stuff. And we're partnered between College of Engineering and School of Medicine. And really our kind of MO is to bring kind of an intersection of robotics, rehabilitation robotics, sensory motor neural engineering, and linking those two together with bio-inspired artificial intelligence. So we're doing things like the Luke arm, which involves estimating what a person's trying to do, as well as providing sensory feedback from this closed loop prosthetic hand. But we also do a lot of things outside of invasive technologies, focusing more on non-invasive tools to target broader patient populations and different types of patients. So we're doing things like thought-controlled exoskeletons or smart assistive devices. We have different types of rehabilitation tools and diagnostic techniques and things like that. And we're really just nestled in the middle of the hospital. So pretty much doing anything we can to take electrical and computer engineering, so hardware, software components, and bring them into patients and really just help with smart healthcare.
Yeah, that's really exciting. And it sounds like University of Utah is really putting a big push towards this. And like you had said, open up a new building, open up a lot of facilities to this. You're actually the first U of U professor that's been on the show. We have had lots of people from Ripple Neuro, BlackRock Biomedical, all this kind of stuff, but never a professor somehow. And but it seems like they're growing a little bit. But you're also a pretty new professor. How old are you also?
Yeah, I started in 2020 or so. So I'm 28 years old, so very young, still getting stuff set up and really kickstarting it. So the grant that we got to kickstart the lab is the NIH Director's Early Independence Award. So it's basically an R01 level funded $1.8 million essentially over 5 years. And that is to basically skip traditional postdoctoral training and accelerate the pathway into research. So I think the average age that NIH states for someone to get an R01 is somewhere around 47 years old for their first R01. And they really want to change that. They want to get people into science earlier. And so that's the mechanism that I went through. And so very fortunate to have that funding to kickstart stuff. And that's how I got started at the U. But yeah, it's been an awesome environment. I've been here actually for a while. So I did my PhD here, and then I did a short postdoctoral study before this grant got funded. And now I'm here as faculty. And yeah, as you mentioned, there's a thriving neuro community here. We have multiple startup companies that have spun out of the U. So both Ripple and BlackRock and Patel and other groups. And then the faculty program here is growing a lot as well. So it used to be just biomedical area, and now it's really sprawled into all sorts of different fields. We have some amazing new neurosurgeons involved, people in psychology, people in neurosurgery, neurology, physical medicine and rehabilitation. Yeah, and pretty much every engineering discipline now is somewhere involved in the neural interfaces here. The community here is really strong and exciting.
Yeah, it's as we were talking about before we started recording, is I'm an alumni of University of Utah. So I feel bad because I'm just like, oh, there's so much cool stuff going on in this field, but it seems like it's growing. So you mentioned that you did your PhD and short postdoc at University of Utah. Is this what you were always working on, this, BCI, brain computer interfaces, or how did you get into this field?
Yeah, I actually started my studies at the University of Texas at Austin as an undergraduate doing biomedical engineering. At the time, the University of Texas at Austin really didn't have much of a neural interfaces, brain-computer interfaces area. It was always something that I thought was pretty cool. I wanted to check that out. You read all these cool stories about things like this happening and wanting to get involved, but there were not really any faculty there. So I just started exploring other areas of machine learning, artificial intelligence in my research. And then I applied to a summer program at the University of Utah and a few others, actually, all over these like research experiences for undergraduates. And I got accepted at the University of Utah. And to be quite honest, I was actually hesitant to go out to Utah. I was like, I don't know. I don't know what's out there. Is it really going to be worth my time? But my sister, who lived in Denver, Colorado, was like, Utah is awesome. If you love skiing and hiking and fun stuff, you will have a blast out there. And that's very up my alley. And the research sounded cool. So I came out and I just immediately fell in love with it and decided to come back and do my PhD there. And I laughed because when I went to Austin, I was like, I'm going to live here the rest of my life when I went to my undergraduate there. 4 years came and went, and I was like, I got to get out of this town. I'm ready to do something new. And the same thing, I said the same thing when I went to do my PhD at the University of Utah in Salt Lake City. I was like, I love Salt Lake City. I'm going to stay here the rest of my life. And 4 years came and went after my PhD and decided, actually, yeah, I am going to stay here. I'm going to find a way to make this work. And that's when I started applying to these grants to see if I can get some funding to start my own research line here.
Yeah, that's pretty exciting.
Hey guys, just a quick pause to talk about our show sponsor, Ripple Neuro and NeuroMed. If you're a scientist looking to get the best quality data possible in your animal and human ePhys experiments, then talk to Ripple. Get a complete solution for your neuroscience research application backed by dedicated support. Be sure to tell them you heard about it on the Neural Implant Podcast. That will really help us out. Thanks. Now back to the show.
I can definitely affirm that Utah is very unique in the world, I think, in terms of outdoor activities and everything that you can do. And you don't know what you have until you lose it. So it wasn't until I left that I was just like, oh, wow, people like travel, people fly for this kind of stuff, go mountain biking, rock climbing, snowboarding in these kinds of places. And so it's pretty crazy. Okay, so you talked a little bit in the beginning about your research. Do you want to go in a little bit more in depth about the different aspects of your research? And maybe we can start with the Luke arm. How does it work? Why does it work? What's the intention behind it? Everything like this?
Sure, yeah. So the Luke arm is a large portion of my doctoral research. And so this is in collaboration with so many people, right? First, I'll just do my due diligence and say that this wouldn't be possible with a ton of people involved. Greg Clark is another faculty at the University of Utah in biomedical engineering who's really leading and spearheading a lot of this. There's collaborations between, as you mentioned, Ripple makes a lot of the equipment that allows us to interface with our implanted devices. And the implanted devices are, of course, made by BlackRock Microsystems, or now Neurotech. Yeah, the idea is that after a person has lost their limb, the biological pathway that would allow them to control their limb and feel from their limb still exists. So if you were to reach out and touch your fingertip right now, you would basically convert a mechanical force on your fingertip into a electrical signal that then goes up to your brain. And our idea is that after a person's missing their hand, that biological pathway that conveys that information about the sense of touch on your fingertips still exists. It's just that sensor that does the mechanical transduction into electrical energy is missing. And so what we do is we tap into the nerve and send electrical current, which then turns into these digital pulses that go up to the brain that a person can interpret as a sensation, as if it was coming from their missing limb. So that's the idea behind the Luke arm, is that you can give a sense of touch back to an individual and create a sensorized prostheses. And the other side of it that's really cool as well is that those same biological wires that provide sensory information can also be used to provide motor information and allow us to control a device. And so in this case, when you think about moving your hand, information is transmitted from your brain down to your spinal cord, to your nerves, which then actually cause your muscles to contract. And then your muscles contract and pull on your tendons that then actually physically move your hand. And so when your hand is missing, there's just nothing to move, but the muscles and the nerves are often still in place and still sending these electrical signals. And so using the same type of devices that would allow us to inject current into the body to stimulate the nerves, we can also listen to what the nerves are doing or the muscles. And with that, then we can try to predict what a person is trying to do. So now this sensorized prosthetic is also controlled by your thoughts. So as you think about moving your hand, we have a computer that listens to these signals and interprets them into say, oh, hey, that pattern of electrical activity in the nerve and muscles is associated with grasping or trying to rotate your wrist and things like that. So yeah, that's a little bit about how the Luke arm works. And now we're leveraging that same technology and moving in a lot of different directions. So one thing that we're doing as a natural extension is take this device and make it more widespread. And we're at the point now where we're doing basically take-home studies. So people are taking this portable device that allows them to control a bionic arm with their thoughts and have a sense of touch back. They're doing this in the home. And very soon they'll be doing it in an unsupervised manner where we set them up and let them just run wild with it. And we're also taking the same type of technology and bringing it into new areas. And that's a lot of the new directions that I'm spinning out as well. So the grant that I mentioned earlier is focused on using the same style of technology for controlling bionic devices and bringing it to stroke patients. So we can provide control of exoskeleton devices in a paralyzed arm rather than a prosthetic hand and a missing limb. But then we also have other interfaces to do things like virtual and augmented reality. And so now we're even partnering with Facebook or now Meta to develop types of technologies and neural interfaces that can be used for applications in the broader commercial market as well, and not just for healthcare applications.
Wow. Yeah, that's really exciting. The hand is very complicated. I think there's 19 degrees of freedom or something like this. But you can also go as low if you just have a hook for an arm or something like this. You could open and close the hook. Where on the spectrum of that is the Luke arm? Is it more opening and closing a hook with a simple movement? Or can you do, I don't know.
Playing a piano, right?
Playing piano, yeah.
That's kind of like the ultimate one. Yeah, if you consider a hook, that's open and close. So that ability to do what we call one motion in two ways. You can open and close, but it's really just one fundamental motion that moves in two directions. We call that 1 degree of freedom. And the Luke arm has 6 degrees of freedom. So what that means is that you can open and close your thumb, you can open and close your index finger, and then your middle ring and pinky fingers are all coupled together. And then you can also move your thumb across your hand. And then you can rotate your wrist and you can flex your wrist. So that gives you 6 different possible movements, which is a lot more than what most people do. But really the key component is from our side, the thing that we're working on is not so much the mechanical properties of the hand, but focusing a little bit more on the way that we control it. And so traditionally you have these advanced bionic arms and you might specify what a person is trying to do. So you could say that they're trying to make a grasp and you could move all 6 of these in a kind of a synergistic way to form a grasping shape. Or you might say that the person is trying to make a point. And so then you can move all of these into a specific gesture to point with the hand. But when you do that, you're basically treating all of them as one thing that you're doing, right? You're moving all of them in one in unison and as a synergistic movement. And what we're really interested in doing is using nerve signals and muscle signals to provide proportionality and independence across all the different movements. So that means that I could move my thumb with some level of proportionality. I can move it part of the way, all of the way, 22% of the way, likewise with all my other fingers as well, and do that in a simultaneous manner. And for the mathematics and data science type people out there, what we're talking about is no longer a classification problem, but a multiple regression problem. So trying to determine the exact position of 6 different things at once. And that allows you to do more complicated tasks like regulating your force and creating novel grip patterns that weren't explicitly labeled in the hand mechanical designs or also in the control schemes. So that's where we're bridging into, and that's a very challenging area. And as you mentioned, the hand is extremely complex. So that's something that we're all still working on.
Yeah, that's really exciting. And actually, the way you described the 6 degrees of freedom, it really doesn't sound like you need too much more. Like you don't need to really ever move your pinky independently. Usually it is moved with everything else together. Yeah, so it's pretty exciting. Okay, so what does it look like for the patients? They're implanted, right? And then there's some kind of training involved. And so what does that look like? What does the process look like for the people? And then I guess how many people have had this implanted as well?
Yeah, so to date, there have been 7 people that have had this implanted for the prosthetic. And there's actually an 8th person who's had Utah slanted electrode arrays implanted in them for a separate reason, which I won't get into now. But yeah, they undergo surgery. It can be a pretty long surgery or so, roughly 3 hours or so of going through this process. Basically in implanting a couple different devices. So we work with BlackRock to do the Utah slanted electrode array, but we also work with other companies like Ripple and Synapse Biomedical, which do these EMG arrays. So they record muscle activity as an implanted device. And then you go through this process. And when you're finished with that, the idea is that it's relatively intuitive and quickly transitions into a usable device. So there's a couple of things we have to set up on our end. The main hurdle being the sensation side. We implanted, essentially hundreds of electrodes into the nerve, and we have no idea what they do until we test them one by one. And so it's this really boring process of stimulating the nerve and then asking the participant, did you feel anything? They say no. So you turn it up a little bit. You keep doing that until they tell you, nope, didn't feel anything. So that one's probably just in some dead space. So some outside of a fascicle or so. And then you go on to the next one and the next one and next one. Eventually they tell you, oh, this one feels like it's a sensation coming from my thumb. The next one might feel like it's a sensation coming from my index finger. It might feel like my wrist is rotating when you stimulate one. So all this type of information, we can get cutaneous information like the sense of touch, like pressure, but then we get in vibration, but we can also get proprioceptive information, which is like the feeling of your hand moving in space or like your joint being flexed or your muscle being tight. And we have to basically map out what all of these sensations are, and then basically create a lookup table that says when the hand moves, you stimulate this electrode to make it feel like the hand is moving. And when the hand makes contact on the index finger, you stimulate, oh yeah, that was electrode 35 that causes them to feel like something's moving on their index finger, on their thumb or index finger, whatever it might be. So that's the sensory side to setting up. That takes some time. And then we also have the control side. So what we call like the motor decode side. And this one's a little bit more straightforward. You have the person try to move their hand in a lot of different ways, in ways that we already understand. So I would say open and close your hand. They attempt to do that a few times, and we record the muscle activity and the nerve activity from these different implanted devices. And then it's basically like an inverse correlation or kind of an inverse lookup table again. So the next time we see that pattern of activity that looks similar to the activity they did when they were trying to open and close their hand, then we just say, oh yeah, that person's probably trying to open and close their hand. That's how we make the hand move. It does take some setup, but the idea is that after the fact, you have this device that is very intuitive. It follows the exact same pathway as would normally be done. So when the person thinks about moving their hand, the hand moves. And when they make contact, they feel sensations from the correct locations that are anatomically congruent.
That calibration sounds tedious. How long is it? Like how many hours?
We can get through an array of 96 electrodes in probably about an hour or two if we're doing this pretty quickly and the person's done it before. Realistically, when you first start out, you can get through maybe half an array or maybe even a quarter of an array in 2 hours, because that first sensation they feel is like super exciting and they don't want to move on. They're just like, wait, let's keep doing this. Let's try this. And then you do all these fun different things. And sometimes you jump into an experiment and let them play around. But yeah, once they've gotten the novelty effect is over and they're just like, okay, let's get this calibrated and get this running full steam, then you can crank through it pretty quickly.
That's funny. And then does it have to be recalibrated over some time? Does the things shift or some things grow in or grow out or die or something like this? How does that work?
Definitely. Yeah. And that's probably the biggest challenge in the field currently. And the Utah array is definitely not an exception in that way. We have a lot of channels that drop out over time. The recording quality goes down over time. The sensations can shift and move. And so, yeah, you definitely need recalibration. Now, how frequently that needs to be can vary a lot. And we've had some times where we can do something and it lasts about a month, which from my sense, I think that's pretty good. I think a person would be okay calibrating their hand once a month. Now, if you have to do it every morning, that's a lot more, right? People won't probably be happy about that. But control wise, you can get pretty good stable recordings from muscles, and those can work really well for long periods of times. And people get more stereotyped in the type of movements they make. So from the control side, I don't really have too many concerns. From the sensory side, there are a little bit more challenges in that things do shift, things do need to be recalibrated. We think roughly about a month or so is where we're at. But it also depends, because in our most recent participant, we had one of 3 arrays that were implanted that was just extremely stable all the way up until we took it out and explanted it. And that was 17 months or so. And we have some speculation as to maybe what caused that stability in that one device, but I think that are particular types of surgical techniques and different ways that maybe we can improve the device and really increase the stability beyond needing to do a lot of fundamental redesign of the electrode technology.
So I remember when I was doing the internship at BlackRock, we talked a lot about like glial scarring and basically encapsulation of the electrodes and everything like this. That was more in the central nervous system in the brain. Is that also a problem in the peripheral nervous system, or is it worse, better? How does it compare, I guess?
Definitely worse. I don't know. Maybe the grass is always greener on the other side. I work in the peripheral nerve, but my understanding is that in general, it's worse. And really the challenge in the peripheral nervous system is mechanical, is much different than in the brain. The brain moves a little bit based on like blood flow. And even if you're like moving your head really back from forth side to side, it can cause some movement in the brain, but it's like small amounts. Now, in the peripheral nerve can stretch almost like centimeters, right? When you have a person just doing this, just extending and flexing their elbow. So it can be very challenging to put a device in that can withstand all the different types of movements that are different types of mechanical challenges that are present in the peripheral nervous system. Immune responses are typically different as well because you don't have a blood-brain barrier, right? So you have this full like immune system response, right? It's like having an infection in your arm and that can spread and all sorts of different challenges. I think most people would say that it's worse in the peripheral nervous system and that there's definitely some bigger challenges there.
That sounds much harder, actually. Yeah, very cool. Okay, so let's talk about this other research too. You said you were working with exoskeletons, basically implementing the same technology, but using different things than non-invasive as well. Do you want to talk a little bit about this?
Yeah, definitely. I think a lot of this motivation comes from patient perspective. And there's been some studies to say what type of technologies people are open to. So Jen Collinger has done a lot of this in Pittsburgh, where they've surveyed spinal cord injury patients to see their receptibility to different types of neural interface technologies. And generally, when you have a pretty severe seemingly non-reversible disability, I think people in general, this is just my perspective, but I think people in general tend to be more open to invasive solutions. So when you've lost a hand, you're not going to regrow it. Like the solution is to get an implanted device that is like state of the art, that really is like the Luke Skywalker arm. Now, with a stroke, what people have is a paralysis. They have a hand. Their hand is still there. They just can't control it either in an intuitive way. It doesn't work as well. And they're going through physical therapy and trying to regain function. And so I think their ultimate goal is to ultimately have their own hand work again, not to have some long-term assistive device or some implanted surgery to help them get their arm back. But I think that this kind of leads to the idea of wanting to do a non-invasive technology for this patient population in particular, right? They have a hand, they just want it to work better. And so what we're trying to do is find ways to do that in a non-invasive way or a non-invasive approach to it that can bring back their lost mobility and dexterity. With that in mind, really what we're trying to do is use EMG, so from muscle recordings from the surface of the arm to control an exoskeleton. And so there's been some very preliminary work out there that's happened. And there's a company now called Myomo that has this exoskeleton device that can do 2 degrees of freedom. It can pinch and it can move the elbow. So moving the elbow is pretty simple, right? You can record from the bicep and the tricep to do up and down. That one works pretty well. Now, when you get down to the hand, all of your hand muscles are just intertwined in your forearm. And so if you're trying to get a general picture of what the hand is doing, if you record from those muscles pretty easily, you can separate flexors and extensors, and that will tell you if they're opening and closing. And you can get this relatively simple controller that can do like normal prosthetics will now, where it's an open close type strategy. So really what we're focusing on here is, can we leverage recent advancements in prosthetic control and just AI in general, so machine learning and artificial intelligence and all these complex regression models and biomimetic models of how EMG activity translates into dexterous control of, like we mentioned earlier, 6 degrees of freedom. So this would mean that the exoskeleton doesn't just open and close the hand, but it could rotate the wrist. It could help the person make a power grasp, so full hand grasp rather than a delicate pinch grip. And the challenges with current devices is that you're trying to record from muscles that are already weak, that have really small signals, and they have spastic signals, meaning that they're firing at times that they shouldn't be firing. They're just doing all this abnormal activity. And so what we're trying to do is use machine learning and AI to find patterns and ways that we can translate that type of activity of muscles into dexterous control of multiple degrees of freedom of an exoskeleton. And then the broader picture is that when a person's using this exoskeleton device, they're thinking about moving their hand. It gets converted into the actual movement of their hand. So similar to that prosthetic system we talked about, but in this case, their hand actually does move. And when their hand does move, again, they're getting proprioceptive feedback, they're getting cutaneous feedback. And so you're bridging the damaged pathway. You're promoting plasticity by having the person attempt to redo these types of movements. And as they do them, they're actually getting feedback from it. And this has been shown to be an extremely effective strategy. So not only does it provide the person with an assistive tool that they can start using immediately around their house, but it also provides them with kind of this personalized patient-specific therapy that is guiding their rehabilitation. So the idea is, you had a stroke, you wake up in a hospital, you get fitted with this bionic arm that helps you move immediately. So it's like nothing happened. And as you're doing these things in your real world life, all of a sudden, you don't need the exoskeleton anymore because your hand's back to use. And that's the long-term vision that we're working towards. But to get there, we're starting with some very basic things by trying to figure out how we can get more dexterity out of muscle signals that are otherwise weak and spastic.
That's really cool. That sounds almost like gamifying this therapy process, and have this, like you said, therapy is a little bit hidden, and the patient might not even know that they're doing the correct rehabilitative exercises, which can be a huge pain. I remember my brother broke his leg when he was a kid, and he had to do these really boring exercises and everything like this. So yeah, that's really exciting. That's pretty cool. Okay, you have basically this invasive and non-invasive one. This is going to be difficult. Choosing which one of your babies do you love more? Which one do you love more?
Yeah, that's tricky. I think they're different in so many ways. I think right now I've focused a lot on moving in non-invasive routes. That's a direction I've been shifting towards in my lab in general, because for a few different reasons. One is that for the patients that we're working with in this case, there's a specific need for some non-invasive technology. The other is that I personally really like having a close pathway to translation. Neural interface technologies, especially if you're doing things that are focused on implants and making new implants and things like that, you can have a very long pathway before this gets used. Even BlackRock, who's been around for a long time, is just now starting to get, these long-term, actually like clinical type drives where, actually, yeah, we're not just making this for research tools anymore. This could actually be a product that patients could use. And so now they've been licensing technology from other groups and bringing this in and making it happen. But there's been so much buildup to that, right? Developing the Utah array, getting the Utah array FDA approved, all of that. The nice thing about using non-invasive approaches is that while they definitely don't offer the same level of specificity and they don't necessarily provide the options of working with all the same types of patients, non-invasive options are not probably going to be great for people with locked-in syndrome. But the non-invasive options provide a much faster route to translation. So we partner with companies that already have existing products. So we're working closely with Myomo, who has this amazing exoskeletons. Patients love it. They have a ton of feedback about how great it's been and how much it's changed their life. And we think that we can leverage the products they have and bring neural interfaces, specifically advanced control algorithms and feedback strategies using neural interfaces and sensory motor neural engineering to improve a lot of existing devices on the market. That's one area. Another thing that we're looking at is, for virtual and augmented reality, but also looking at things like assistive technology. So you can use muscle activations that you are able to do for like spinal cord injury patients to control devices. So I'll do a quick aside on that one, which I think it's really fun to talk about. We have a program at the University of Utah called Trails Foundation, and it's about bringing people back into basically recreation after spinal cord injury. So we work closely with a company spin out of the University of Utah called the Tetradapt, and they've built a ski that you can sit down in and you can control it with basically sipping and puffing air. So these are complete spinal cord injury patients who can't, move anything really but their neck and blow into this straw. And if they breathe in, they can turn the ski to the left. And if they breathe out, they can turn the ski to the right. So they're skiing down mountains. They're actually doing this now. And it's an amazing event where you can watch them do races and all these cool things in this type of technology. But it's not easy to ski down a mountain as you're like sipping and puffing. And as we translate this into new technology, which is currently happening as well, you can do sailboats. And you can, if you've ever been sailing, there's so much more going on. And so they've basically created like a Morse code strategy of sipping and puffing to allow you to control these complex recreational sports. And our idea is that that's a prime target for non-invasive, approaches that we could work with and have something available for them immediately. Brain computer interfaces, like patients still have access to their neck muscles. So why not use their neck muscles, or even just put like non-invasive sensors all over their body that allows them to come up with their own control scheme besides just breathing and sipping air. That's the idea moving forward. And to get back to your original question about, whether or not I have a preference in the types of technology. Obviously, they're both great and they have different patient populations, but I do think that there's a lot of room for innovation and clinical translation now that can happen with non-invasive technologies. And ultimately, I think long-term vision, I think that what we'll be able to do with invasive technologies will hopefully ultimately translate to any non-invasive technology. We're probably not going to have single unit recording, but long term, I think we'll get away from, as the resolution and speed of just broader non-invasive technologies become more realistic, I think we'll get there.
That's exciting stuff. I looked at the TetraDapt website, and yeah, there's a lot of interesting stuff. But what you were talking about is puffing air, and while you're doing physical activity, doesn't really make sense because you should be breathing, not necessarily trying to control this. So you got to have something that you can breathe in parallel to do this kind of stuff. But that's really exciting stuff. Do you have a history of family or friends or something like this that are paralyzed or something like this? Or what's especially motivating you to deal with this specific patient population?
Yeah, I think a lot of people have some motivation behind that. I have a lot of students that say something along those lines of, I had a family member with a stroke or a family member with amputation or a friend or something that drives them into there. I personally don't actually have a connection directly into it. I got into this field because I was interested in just the possibility and the type of technology. But I think there's one particular case that did resonate well with me and further solidified my decision to wanting to work in this field. And it was working with one participant who was talking about having lost their hand. And they said that losing a limb is like losing a family member, except you're reminded of it every single day. And I actually lost both my father and my brother when I was a kid. And I remember how devastating that was. But I can only begin to imagine the type of challenges that would come even beyond that. When you're talking about now you have chronic pain, you have non-autonomy in your life, you have all these other challenges that are associated with it. And every day you're reminded of your loss, right? Because of these challenges in your day-to-day life. And I think that really just stuck with me. And that really, seeing the impact this type of technology can have on patients. Obviously, it's way cool. We're talking about like sci-fi futuristic things. Who doesn't want to work on the Luke arm? But seeing that it actually helps patients as well, and seeing their days get brighter and their smiles come back to their face, that's really a very rewarding part of it for me.
Yeah, definitely. I think especially if you have the chance to meet the people, then that's huge. I know that a lot of these neurotech companies are making it a bigger point that the employees who are actually assembling things or writing code or whatever, that they actually do meet the patients involved, because that can be a huge boost. And it's not just some abstract concept. It's actually something where it's affecting positively the people that, so if you work harder, the people will be happier too. So I want to talk a little bit about your youth. And basically, I don't think I've ever interviewed such a young professor, and it's really reminiscent. 28, and I guess you were 26 when you first started the professorship, or no?
Yeah, 27.
27, okay. Yeah, that, like what you're talking about, that really doesn't happen anymore. I heard about that a lot in like the 50s and 60s, because there were just so few PhD graduates and so many faculty members out there, and they're just really quickly hiring and everything like this. And I don't know, do you have any tips for people who might want to follow in your footsteps, or do you think it was just kind of luck because this NIH has this new program with the R01s, or what advice can you give to people wanting to follow in your footsteps?
Yeah, so I think two pieces of advice that I would give. One is there certainly is a matter of luck, right? You need to be in the right place at the right time, doing the right things. And that's certainly true. That being said, I think you can bias luck in your favor in a lot of ways by being very proactive and having a long-term strategy with multiple avenues for success. Your grant's not going to get funded this round, so you're prepared to submit the next round. That grant mechanism isn't going to be the best one for you, so you're planning for a different one. And so in my case, what I really was focusing on was, I knew I wanted to stay at the University of Utah, fell in love with Salt Lake City, wanted to stay here. My partner's here and her family's here. So we wanted to make it work. I knew I wanted to go into academia. I knew I wanted to do research. And so I was very strategic about what I was going to propose and how I was going to do it. So generally saying, you can't just follow in the trails or the footsteps of your PhD advisor. So I knew I had to branch out. I knew I had to do different things. So that was the idea of going into stroke rehabilitation, particularly, was also not only because I was in this new hospital where new people were involved and different patients, but also, trying to be strategic about how can I differentiate myself from others? What's a new scientific niche that I can fill? So that was one strategy. And then I had outlined dozens of grant mechanisms that I was planning to apply to, because what I had seen is this more and more now, the people who get interviewed at faculty candidate positions are people who are coming in with K99 R00s, right? Which is that kangaroo award, which is basically 2 years of R01 funding. And then that kind of provides a big boost and incentive to hire these people because they've already gotten funding behind their belt and they're likely to continue to do that moving forward. That kind of brings me to the third piece of advice, which is, unfortunately, money talks a lot in an academic sense. And so having funding and showing that you're successful to manage a lab and keep people moving forward from a funding standpoint can really be the deal breaker. And it certainly is luck on getting that funding and being strategic about how do you target that funding and finding the right opportunities and seeking the right advice. But ultimately, if you can get some funding behind you, I think that there's many avenues you can take. And whether it's a tenure track position in a state university where there's a lot of state funds and you do a lot of teaching, or if it's just, hey, I have my own funding, I'm looking for an adjunct type position in a school of medicine where I just basically am going to fund myself entirely from my grants. These, what we call like soft money positions, are very doable if you come with some money. And I think that the biggest piece of advice is to think about that early and think about it often and try to get your ideas funded, because the unfortunate reality is that science is expensive. and if you can't convince a faculty or a university to pitch in the money to help you show that you can get more money, then the other option is to try to get a funding agency to support you early on and then leverage that to find a faculty position.
Yeah, definitely. I've heard that essentially when a company or a university hires you, they're taking a risk, right? They give you startup funds, they pay you a salary, and they could be out $500,000 or $1 million or something like this, and you might not bring anything back. So if you are able to show that, okay, I've brought a portion of this, a sizable portion already, and so it really reduces the risk on their side. So that's pretty clever. This isn't something that is often taught for your PhD, is it? I haven't necessarily heard this. And how similar is your training between what you're doing at the PhD, working at the bench, versus being a professor and needing to find those dollar bills, chase them down?
Yeah, it becomes very different for sure. As a PI, everyone structures their lab in different ways. And a lot of times you still can go and work at a bench. And some of the most rewarding times of being a PI is that you get to train students, you get to work at the bench with them and bring them up. If you're also teaching and you're also serving on committees throughout the university, and you're also consulting and running your own startup and doing all these other key components that most faculty do, then your time gets limited really quickly. And what ultimately you end up focusing on more than anything is making sure that there's a successful environment in place for your team. And so really what you become is a fundraiser and a project manager in a way. You're going around, you're bringing in the dollars to keep the research going, to keep your personnel funded and allowing them to do research. And you're keeping them on track in the broader scope of things and connecting them to the resources they need to be successful. So it's very much being in an early stage startup where what you're doing is constantly trying to bring in that first Series A type funding, where you're just constantly trying to connect with new people, new funding agencies, and bringing in dollars to support your team and let your mission move forward. I think right now, there's been a lot of mixed feelings. Some people say that scientific funding is harder and harder to get these days, and that R01 success rates are now down to 10%. But they've also been going up. I saw recent things that NSF funding rates have gone up. NIH has some pretty high success rates in certain categories. And I think right now, in particular in the area of neural interfaces and in the area of assistive technology, I think funding is pretty hot. I think, things have started to come out of this research in very promising directions. And I think one of the greatest indicators we've seen so far is now the corporate interest in this area, right? So we're talking about large Series A for companies like BlackRock. We're talking about Series A funding from all sorts of different ones. And, people love him or hate him, Elon Musk, in a lot of ways, he has revolutionized and brought public attention to the area of neural interfaces. And so for that matter, I think I'm very grateful that we have a lot of new companies getting involved in this area. And I think even when I bring students in now, it's a very different conversation than when I was a student, where it was just like industry versus academia. Who are you going to work for in industry that does brain computer interfaces? And now I can name I can name dozens and hundreds of neural interface technology companies, which is way cool, very different. And I think that really fundamentally has changed in like the last 5-10 years.
Yeah, definitely. There's an explosion of this, and it's all synergistic. I think you do need, it needs to grow along with each other. And then you have some companies fixing the problems of other companies and blah, blah, blah. Yeah, that's really exciting. So having had a glimpse into both of these worlds, what's something that maybe PIs or PhD students should be doing more as they're finishing up, or what specific exercises besides buying dozens of grant mechanisms and writing everybody what you did, like what would be maybe a more general assignment or something like that?
So I think ultimately if you really do want to go into academia, that's what we're talking about here, specifically advice to help people in that.
Yeah, I mean, I would argue that funding is important regardless of where you go. I'm sure you could be hired on as an engineer, but man, if you're an engineer that can bring on money as well, that has got that magic grant pen, then you're that much more valuable.
Oh yeah. So I know multiple people in industry that have either do grants on the side just because they have a small project that the company can't necessarily fund from a commercial perspective, but would be happy to allocate resources towards. And then there's companies like BlackRock who are specifically hiring grant writers. And that's a very common thing as well in early startup type companies. So yeah, so I think funding is very important, but I think more than just like getting funding is the idea of sustained success. A one-off grant is great. That's luck. If you get one thing, that's luck. But repeatedly being successful in funding starts to show a pattern of success it becomes more and more unlikely that it was just luck. Starting early, I have all of my undergraduate students in my lab apply to undergraduate research fellowship awards, right? These are like, I think $1,500 for the summer to help them, like $10 an hour, which is challenging to live off of in most cities these days. These things help and they add to your resume. It's not going to cover your student tuition loans or things like that you might need, but they start to show that, yeah, you can get funding for your ideas. So starting at an early stage, then you get to graduate level research fellowships, also conference awards. And so you can get like travel awards at conferences. You can get graduate research fellowships like the National Science Foundation or the NIH fellowships. Then they have postdoctoral awards. And so each time you get one of these, you set yourself up and you're also learning grantsmanship along the way because they have different agencies that have different requirements and different ways to write. And so, yeah, going through that whole process is incredibly important, and just learning how to navigate and read a solicitation and know what they're looking for. That would be a key thing. And then just other broad advice that I would say that's really important is, I think almost in every career path, with a few exceptions, as you go higher up the chain, you become more of a manager and less of a technical implementer, right? So you start managing teams, you start directing people, you start doing bigger picture things and less on the smaller micromanagement or on the like technical implementation side. So in that sense, one of the things that I make all of my PhD students do, at least try once, is to mentor an undergraduate student. So it's a great experience for them. If they don't like it, I'm not going to require that they like mentor undergraduates, but I've had students that have 10 undergraduates under them and just love it and love to be more of the project manager style. And that really does set you up for success in a lot of different avenues as well. So if you come into a company and you're a team lead, then having the ability to manage people and direct them and work together in unison and build team camaraderie and all sorts of different things like that are really important. And in academia, it's incredibly important to be able to say that you've mentored students. And if your students have gotten an award, so now you have a graduate student who has a fellowship, but not only do they get a fellowship, they help their undergraduates that they're mentoring get fellowships. Then, it starts to build this really good track record of, I can get funding, I can keep my students funding, I can keep a sustained research program. And that's a pathway that you start to build. So I would say there is definitely a reason as graduate students to focus a little bit more on some of these, what a lot of people would consider like tedious administrative challenges, right? Managing students, like trying to get schedules to align, making sure that the students aren't fighting over equipment, things like that. But resolving conflicts, managing people, finding money and doing budget analysis and things like that can actually be very important skills that I think no one really wants to do when they're doing awesome research like brain-computer interfaces, but they're also very fundamental skills that will help push you forward into higher career stages.
I guess it's welcome to the rest of your life. If that is something that you're going to be, it's going to be something that you're going to be doing more and more of. I think you're absolutely right that the higher up you go, you're more of a manager and less of a hands-on person. The problem is, though, if you don't like it and if you're really good at it, then people would be like, wow, this guy's really good at it. And we should put more things on his plate that are exactly like that. Then you might be digging yourself into a hole. So that's another thing, I guess, is only be excelling if you're like it.
Yeah. Or conversely, find a mentor who has a little bit more support of your personal interests, not necessarily just your amazing skill sets.
Yeah.
But trying to find an area where, you feel safe doing what and allowed to do the fun things that you want to do, and not necessarily the things that you're best at or the things that are easiest for you versus someone else.
Yeah, that's a good point. Cool. Dr. George, this has been excellent. I've really enjoyed this. Is there anything that we didn't talk about that you wanted to mention?
I always like to say at the end, just shout outs to all the people who've helped. In particular, you always got to start with the patients, right? They make all this stuff happen. They're volunteering to get involved in research. In some cases, they're physically donating their body to science with an invasive surgical procedure. And in the end, they don't get to keep the device. The Luke arm goes home, back to the research lab. The exoskeletons go back. And so it's really not for selfish reasons they do this stuff. It's all for the altruistic reasons of helping others and advancing science. So many shout outs to them. And then also just all the people who've been involved and helped our research, companies that we've already talked a little bit about that have been super involved, as well as just collaborators at the University of Utah and just broader institutions as well. Yeah. And thank you for having me on and allowing me to share some thoughts and chat about some cool stuff.
Yeah, thanks. It's been fun.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.